today and on Friday, I'm going to be talking about the physics of magnetic confinement fusion. And as this sort of Twitter-esque title for the talk is meant to indicate, necessarily that's going to mean that some of the content I'm covering is going to be somewhat superficial, right? There's no way I can go into great detail about all of magnetic confinement physics in 2 lectures. This often involves an entire graduate program of lecture courses. So what I'm going to try to do is basically give those of you in the audience who have little to no understanding or experience with the physics of magnetic confinement fusion an overview of sort of the major physics issues that we're facing. And by the end of the talk on Friday, I hope to have advanced at least a little bit into some advanced topics so you can see kind of cutting edge research that's going on in at least bits of fusion today. So, as far as I'm aware, this is the only talk which is not on astrophysics during the summer school. And so I thought that it would be useful to start out by trying to illustrate how magnetic confinement fusion, or MCF plasmas, fundamentally differ from astrophysical plasmas. And so you can see how they differ here. What I'm showing you on the left-hand side is an example of an astrophysical plasma, the sun. And over on the other side here, I am showing you a magnetic confinement fusion plasma. Okay. So what's the difference? You can't see it, yeah? And so you can't see it in this case because the sun is about 1 billion times larger than the magnetic confinement fusion plasmas that we have here on Earth, right? And as a result of that, this huge difference in the mass means that in astrophysical objects, of course, gravity is all-powerful, right? It sets basically a hydrostatic equilibrium for the system, and then sort of the magnetic field in the plasma responds to that, right? Whereas in magnetic confinement fusion plasmas, we don't have any such luxury of having a large gravitational field to confine the plasma, and so we have to work very hard with magnetic fields to confine that plasma. And the result is that the gravitational force is completely negligible in these magnetic confinement fusion plasmas. So whereas you had hydrostatic equilibria for the most part in astrophysical systems, we're going to have inherently magnetostatic or magnetohydrostatic equilibria in magnetic confinement fusion plasmas. Okay? And since this strong magnetic field is what's required to confine the plasma, it means that the ratio of the plasma pressure to the magnetic pressure is necessarily going to be at least less than 1, and it turns out much less than 1. Okay, so this plasma beta is going to be small. And in most astrophysical plasmas, that's not the case. Of course, I've shown you just about the only example I know of, the solar corona, where the beta actually is small. But otherwise, beta is sort of order unity or large in astrophysical systems. Okay, so I've cheated you of a picture of a magnetic confinement fusion plasma, so I'll remedy that now. And what I'm going to show you here is a little video. And this video is showing you, if you can see it. Can you guys see any of that? Sort of, kind of. This white light that you're seeing here is visible light, which is emitted by the relatively cool dilute plasma at the edge of a magnetic confinement fusion experiment. Okay? So this experiment, this is a so-called spherical tokamak. This is based in the UK. It's called MAST. There's actually a very similar experiment here at Princeton called NSTX. And the first thing you should note is that I've called this the cool, relatively cool dilute edge. Of course, in a fusion plasma, what we're trying to do is we're trying to take some hydrogenic gas, we're trying to heat it up to temperatures hotter than the sun so that we have enough thermal energy in the nuclei so that those particles in the tail of the distribution have just enough energy to overcome the Coulomb barrier. They can tunnel through the Coulomb barrier via quantum effects, and we can get fusion to happen. Okay? That's basically all the nuclear physics I'm going to talk about. Everything else is going to be plasma physics. So all you need to know is we want the plasma really hot in the middle so we can get fusion to happen. Okay? Now, of course, at the edge, you don't want it to be quite so hot. These plasmas get up to be hotter than any spot in the sun. And so any material wall is going to be melted. So necessarily, you're going to have a relatively cool plasma at the edge. You're going to have strong gradients in things like density, temperature, and pressure across this plasma. Right. So what's the other main thing you kind of see whenever you look at this? The shape of the plasma is toroidal, right? And so over the course of this talk, I'll tell you why that shape is toroidal. You can see also, this is about to die, I'll restart it. Maybe. There we go. You can also see that occasionally you see little striated lines, these bright lines, which wrap helically around the torus, okay? This is plasma which is tied to magnetic field lines. These magnetic field lines don't just go sort of this toroidal way around the device. They also go this short way around the device called the poloidal direction, which I'll talk about more later. And I'll explain why these magnetic field lines have this sort of helical shape to them. What else do we notice? There are long stretches of time in this movie where the plasma basically just sits there. Nothing happens, right? So this means that we have a fairly decent equilibrium in the system, where the plasma is nice and confined. And so we're going to work very hard in magnetic confinement fusion plasmas to obtain such equilibrium. And then occasionally you see these big bursts, right? These are massive macroscopic MHD-like instabilities which disrupt the plasma. So again, we'll talk about where these instabilities come from and kind of what physics is driving them. And finally, even when it looks kind of like nothing's happening, you can see little flickering of the magnetic field lines. And these correspond to turbulent fluctuations of the plasma. Okay? And so even whenever we have an equilibrium situation, we really have some slow leakage of particles and heat out of the plasma due to this turbulent fluctuations. And so basically all the time on Friday is going to be devoted to understanding how this turbulent transport works.
Is this real time?
This is not real time. So in an actual kind of advanced Tokamak experiment, what you'd expect to have, you'd hope for a confinement time on the order of a second, okay? This is not an ideal, this is not even giving you a confinement time of a second. So this is a much reduced series of snapshots. But the idea is that in general, in a fusion reactor type environment, that sort of equilibrium state would last on the order of seconds. Okay. So here's an overview of what I'll be talking about. I want to start out by reiterating this disclaimer. Because there's so much material, I'm going to have to skip some of it, right? So for instance, I haven't said anything to you about how we're going to heat up this plasma, and I'm not going to say much of anything to you. Basically, you can run a current through the plasma, and because it's a conductor, but it's not an ideal conductor, there's some resistivity, and that'll give rise to an ohmic heating in the plasma, which takes you about a third of the way up to the temperature of the sun. And after that, we have to do other things. We have to work harder. We can shoot waves in, for instance, and use resonances with the particles to heat up the plasma, or shoot neutral beams in with very high energy to collisionally exchange with the plasma. But I'm not going to cover that topic in any more detail. There's going to be a lot of topics which are left out. And ultimately, some of the things I focus on are because that's what I'm interested in, right? So today, what I'm going to be talking about first is single particle confinement in the context of magnetic confinement fusion. And so Matt talked about a lot of this on Tuesday, so yesterday, and so I won't spend a lot of time here, but I'll at least put it in context. I'll talk about what sort of magnetic topology is allowed, just from the fundamental equations of motion that we have, how we obtain this plasma equilibrium, and whether or not this plasma equilibrium is going to be stable to large-scale sort of macroscopic MHD type perturbations. And then on Friday, I'll talk about this turbulence and transport that we saw in the movie. So I assume you guys are familiar with the basic concept of magnetic confinement. If you don't have any magnetic field, if we don't have any gravitational field, then these particles are going to be moving around with sort of thermal fluctuations. And so there's going to have disordered motion. Each of these particles is moving with some speed, which is typically the thermal speed associated with the temperature of the system. If we apply some magnetic field, then we know that the particles are going to stream along that magnetic field. They'll gyrate around the magnetic field, and they're going to gyrate with the radius, this gyro radius, which goes like the speed at which they're gyrating over the frequency at which they're gyrating. And if this characteristic speed is like the thermal speed of a particle, then we can see that the gyro radius, roughly speaking, goes like the square root of the plasma beta. So already, in a hand-waving kind of way, you can see why low beta is where we end up getting pushed in a magnetic confinement fusion plasma, simply because the smaller these gyro orbits go, then sort of the better confined you are across the magnetic field, right? So a confined system is going to have gyroradii which are much smaller than the system size in which you're confining things. Now, of course, the problem with this is that you're confined in 2 of the 3 dimensions, but particles are free to stream in the 3rd dimension along the field line. And so we have to come up with some way to treat this. And again, Matt touched on one possible way to do this yesterday when he talked about magnetic mirrors. So again, the basic idea with a magnetic mirror is if you take a particle and you put it into a field which looks like this. So in other words, you can run currents at a couple of different points in the plasma that will increase the magnetic field strength in these regions, and you'll end up getting what looks like a magnetic bottle. So particles will move from low magnetic field region to high magnetic field region, where it will bounce and the particle's confined, right? And so, for instance, that's what happens in the Van Allen radiation belts. Charged particles come in, are trapped by the Earth's magnetic field, and because the Earth has a dipole magnetic field, the field is stronger at the poles, and so particles basically just bounce back and forth between these poles while processing around the Earth, right? And so again, I'm not going to spend much time on this because Matt did a good job of explaining it yesterday. Basic idea being that if you have a charged particle moving from a region of low magnetic field to high magnetic field, and you look at its Larmor orbit or gyro orbit, then you'll see that at these locations, if you just calculate what the Lorentz force is, here you have a velocity into the board. Here you have a magnetic field, which looks like this. So you kind of go into the board, do your cross product, and you find that the force points in these directions. And this force will give rise to both grad B drifts, as Matt discussed, and also some component of the drift, which is along the central magnetic field line, right? So you have a net force, which is pushing particles away from the strong field region. And the other way of saying this was showing that the magnetic moment is approximately conserved as long as the magnetic field is changing slowly over the time scale of the gyro orbit. So in any case, what we're left with are particles which are bouncing in these changing magnetic fields. And you can get a feel for how many of these particles are actually going to bounce by using the conserved quantities in the system. So we can write the parallel speed of the particle in terms of its energy and its magnetic moment, which are both conserved along the particle's trajectory. And there we have the magnetic field, which is changing along the particle's trajectory. So whenever B parallel goes to 0, that's when the particle is going to bounce. And so at that point, the left-hand side is 0, and so you have a balance between energy and mu times the magnetic field at that bounce location. So I'll call that Bmax. And so another way of casting this is going to be writing it in terms of the perpendicular speed of the particle at the minimum in the magnetic field, somewhere over here. And what you find is that the ratio of the perpendicular speed to the total speed of the particle at that Bmin location has to be bigger than the ratio of the minimum magnetic field to the maximum magnetic field if that particle is going to be confined by the mirror, right? So that seems perfectly fine. If you have a big variation in the magnetic field strength, then a lot of the particles are going to bounce. The difficulty is that not all the particles are going to bounce, okay? And while it may seem like you might be able to make this a small fraction of the particles, these particles are just directly streaming out of your confinement configuration. And once these particles stream out, you'll get structure in the distribution of particle velocities, and collisions will then smooth out these structures, and so more particles will be lost, all right? So in the end, even though sort of the direct losses may be a small fraction of the number of particles, it's still not acceptable as a way of confining the plasma, because eventually you'll lose a lot of plasma this way very quickly. So we move away from the idea of these magnetic mirror confinement, and we think about the other way we might be able to confine the plasma. And that's to make sure that the magnetic field lines themselves don't actually touch the boundaries of whatever containment device you have, right? So in other words, the magnetic field lines themselves need to be confined to some finite volume. So there's a famous theory from algebraic topology called the Hairy-Ball theorem. You can't make this up, in which what you find is that the only way to have confined trajectories of a vector field is for tori, okay? The way to illustrate this is to say, imagine that you have some kind of sphere, and you have, say, hair sitting on the surface of that sphere, and you try to comb that hair flat, right? So you can these hairs kind of as the vector field, the local vector fields, and you want to make this flat everywhere, tangent to the surface of the sphere. And you can't do it. You always end up getting some tufts of hair at some points on the sphere, right? So a spherical confinement kind of configuration just doesn't work. And on the torus, on the other hand, you don't have any such problem of having these tufts. And so in the end, what we want to come up with are magnetic field geometries which in some way are confined within toroidal volumes. All right, so that's why the plasma that you saw earlier was a torus. So there are a few different ways we can make these toroidal volumes. Basically, they correspond to 1D, 2D, or 3D shapes. So first of all, you could have a magnetic field line which just goes around and closes on itself. Okay, that's the 1D case, which I'll consider here in a minute. You could have surfaces, so you could have field lines which go toroidally, so the long way around the torus, and say poloidally around the torus. And after many, many times, they never connect on themselves, and they ergodically map out a toroidal surface. So I'll show you pictures of these in a few slides. And the other possibility is where you have field lines which wander over the volume of the torus and map out toroidal annuli. Okay? For obvious reasons, this is not particularly appealing because you still have radial excursions of the particles just by streaming along the field lines. And then if you have any other processes, so far all I've been talking about is single particle trajectories, but for instance, if you put it in two particles and the Coulomb interaction causes those particles to effectively collide, then you can imagine that you can move a fair distance radially just by moving along a field line, and then a collision can move you onto the next field line, which then moves you another distance radially, and so this process limits the confinement. So we're really ideally looking for 2D or possibly 1D configurations. All right, so what's the simplest possible idea? It's just to say, let's imagine we have a wire, I'm going to run a current through that wire, and when you do so, we know that the magnetic field, due to this current, is just going to be inversely proportional to the distance from that current. So here R is just the distance in this sheet. Right? So we have these concentric magnetic field lines where the magnetic field strength varies radially. And we know if we have a gradient in the magnetic field, Matt showed it yesterday, that you're going to have drifts. Okay? So in particular, if I look at a charged particle, I'll take a positively charged particle for definiteness here, then it's going to try to undergo this Larmor motion, so gyro motion about the magnetic field, which at this point is pointing out of the board. But because the magnetic field strength varies over the orbit, you find that locally the radius is smaller here and larger here, and so it drifts upwards. Right? So this is not good. We're not confined in this case. Particles drift across the magnetic field line vertically. And it's even worse than this because if you look at the electrons, they drift in the opposite direction. So you get charge separation, you get electric fields which arise, and this gives rise to new drifts. So if you have an electric field pointing downward, you cross out with the magnetic field, you now have an E cross B drift, which is outwards. So basically, if you try to put a particle in this kind of situation, it's going to drift vertically, create an electric field. This electric field is going to tear your configuration apart. Okay? So this doesn't work. So what can we do? Well, the solution is to add a twist to the magnetic field. So instead of just having a simple sort of circle or toroidal shape here, we're going to include a so-called poloidal field going the short way around the torus. All right? And so just while I have this up, I'll tell you a bit about how you might actually create such fields. Before we knew we just had a single current carrying wire, and that created our circular magnetic field. Here, in practice, we do something very similar. You have these so-called toroidal field coils, which we just run currents through, and you can see that for the most part, this just means that you have a current going through the center of your torus, and so this predominantly generates your toroidal field in the plasma. And to get this poloidal field, there are various ways you can do it. You can try to do it by having very complicated coils here, which don't just go around the device like this, but have some kind of funny helical shape to them. These are called stellarators, and I'll talk about them a bit more in a minute. The other way to do it is try to run a current through the plasma itself. Right? So if you run a current through the plasma, as I said earlier, this is nice in one sense because it heats the plasma via ohmic heating, and it also is going to provide you with this poloidal magnetic field. The difficulty with doing this is that how do you induce this current in the plasma? Well, you can do it with a transformer, for instance. So you take some coils here, you ramp up the current going through those coils, and when you do so, it induces a current in the plasma by changing the magnetic flux in time. Okay? And so inherently, this is not a steady state system. You can only ramp up the current so much before you just can't ramp up the current anymore, right? So this is a disadvantage of the system, but it's kind of the usual system that people use. It's called the Tokamak. And so in this way, we get both poloidal, which I'm going to associate with theta, and toroidal fields in the plasma. And so why is this good? Why are we going to all this effort? Well, if I now imagine taking a cut of my torus, so now if I take this circular shape and I rotate it about this vertical axis, then that gives me my torus. And if I look at the motion of a charged particle moving along that magnetic field line, what's it going to do? Well, it's going to move toroidally, so like this, but it's also now going to move the short way around the circle. And so I just want to look at the motion projected onto this plane. So the particle, in this case, is going to be drifting, due to the magnetic drift, downwards, off the perfect circular trajectory. Right? So in the upper half plane, it drifts off this circular surface. But as you come back down to this point and go into the lower half plane, then it keeps drifting downwards back onto the surface again. All right? So what happens is if these particles actually sample an entire toroidal surface, then you're going to find that there's no net drift. Okay? So the poloidal magnetic field allows us to have no drifts of these particle orbits. All right? Now, it's not quite so simple, because as I said, we have a current running through here. The magnetic field drops off as you go radially, and I've now introduced a poloidal field, so particles move along a field line from out here to in here. Right? The magnetic field strength varies between here and here, so the magnetic field strength changes as particles move along the magnetic field line. Right? And so as we saw before with the magnetic mirror, this means that some fraction of those particles is going to bounce, and it's just going to execute trajectories which look kind of like this. Okay? So a particle will start to move along the magnetic field. Its v parallel will go to 0 because of the change in the magnetic field strength. It bounces, and there's no guarantee that this, because it's not sampling an entire surface, there's no guarantee that any symmetries exist which will make this orbit close. Okay? So in the general case, this orbit just bounces around and exits the plasma at the magnetic drift speed. And so how are we going to overcome this? Well, at this point, I'm afraid I'm going to have to talk a bit more about geometry because, well, it's necessary here. One of the big issues one finds when dealing with magnetic confinement is that much of the physics is not any different than what you'd see in astrophysical plasmas. But the huge complication is the fact that you have to deal with this toroidal geometry. Okay? And so I'm trying to be as gentle as I can with the toroidal geometry in this talk, but there's a bit that we're going to have to do because it simplifies the calculations considerably. So in addition to this poloidal and toroidal angle that I introduced to you before, sort of the third coordinate that we can use to specify points on the surface of this torus is usually either what's called the poloidal flux or the toroidal flux. Okay? And so those are illustrated visually here. So the toroidal flux is just the flux of magnetic field lines piercing this circle, right, which is bounded by the toroidal surface that you're interested in looking at. So basically, this toroidal flux passing through a toroidal surface gives you a label for the radial coordinate inside the plasma. Right? You could instead choose, for instance, the poloidal flux, which is the poloidal flux passing through this ribbon in the plasma. And these are both used commonly in fusion, and I'll use them at different times. I'll use different labels whenever it's most convenient. Okay? But you should think of there's a radial coordinate, which is some psi-like thing, poloidal coordinate, and a toroidal coordinate. And this is the major radius. It's the distance from the middle of the torus out to the point on the plasma. Okay? And that's basically all the geometry I'm going to go into. Okay? So how are we going to get around this problem of trapped particles just drifting out of the system? So there's something called Tamm's theorem, which tells us this is not going to happen if you have an axisymmetric torus. Okay, so in other words, if the magnetic field strength doesn't actually vary as you move toroidally in the plasma, then everything's going to be fine. Okay? And so this is the proof of that. Physically, what's happening is that if you have a degree of symmetry in the problem, then you have an associated conserved quantity. Okay? And so in this case, we have axisymmetry, so nothing's changing in the toroidal direction. And so the canonical angular momentum associated with that direction is going to be conserved. So I can write that angular momentum in this way. Major radius mass of particle times the speed in the toroidal direction, plus this term which involves the vector potential. Right? So A sub z is the toroidal component of the vector potential. And so this has to be a constant in our torus. turns out, I'm not going to go through the algebra, but you can write this colloidal flux function that I showed you before in terms of this magnetic vector potential. And when I do that, what I find, and I just manipulate this equation, then I find that there's some quantity psi star, which is just the toroidal magnetic flux minus this function of the toroidal speed, which has to be constant over the particle's motion, right? And if you look at the size of this, taking v sub zeta, so this toroidal speed, to be roughly the thermal speed, and you just look at how big this is compared to this term, you find it's quite small. It goes like the Larmor radius over the major radius of the plasma, which, if you recall, has to be a small quantity if we want things to be confined in our system. So in other words, this tells us that psi star is a constant, psi p, the toroidal flux, is approximately constant as well. So in other words, whenever particles are moving around the torus, they stay on the same toroidal surface in the plasma, right? So in other words, there's no net drift of the particles across magnetic field lines. So this is known as Tamm's theorem. And it's a good reason to try to go to axisymmetric tori, which are known as Tokamaks. And so in this kind of case, what you have is that particles do bounce, but again, they bounce and stay on the same surface on average, right? Now, again, this direction toroidally is a symmetry direction, so they're free to sort of precess around toroidally however they wish. It turns out things are not quite as restricted as I just said. You don't have to have axisymmetry. You could introduce other types of symmetry into the system. For instance, helical symmetries will also satisfy the same property that there's no average radial drift. And you can show this fairly simply. Again, we define some analogous quantity to this psi star that I defined on the last slide in terms of the toroidal flux and some function. I is just some function of the toroidal flux, so it only depends on radius. And this thing is, you take it to be a size b over r, okay? And so this term is actually going to be small compared to the toroidal flux. So what we can do is we can see, is this quantity conserved? And if it is, then again, psi toroidal is conserved, and so particles are not going to move off a flux surface. So I can write the total time derivative of this quantity like this. So this is the Lagrangian time derivative, or the derivative as you move along with the particle orbits. And this is just the sort of the rate of change at a fixed spatial location of this quantity psi star, which, if our magnetic surfaces are fixed in time, isn't going to vary. And then we have basically the motion of the guiding center dotted into the gradient of psi star. So this is 4 different terms. I'm just expanding out all these expressions. This is 0 because the toroidal flux is constant along surfaces mapped out by the magnetic field lines, right? So in other words, if I take the unit vector pointing in the magnetic field direction, which this v parallel points in that direction, and dot it into the gradient of the toroidal flux, this has to vanish. Right? This term is small in this expansion rho over r because the drifts are slow compared to the thermal speed. And so we're only left with 2 terms. And I'm not going to go through all the algebra, but basically you can use various vector identities to write these terms in a very simple form. You can factor out this common term here. And so this will vanish as long as what's inside the brackets here vanish. And therefore, this toroidal flux is going to be a constant if your magnetic field satisfies this property, okay? Which this property turns out to mean basically that you have a symmetry in the problem, a helical symmetry, okay? So in this case, there's also no average drift of the particles. So this is good. What it means is that we can, in theory, at least come up with a magnetic configuration which is toroidal, it has both toroidal and poloidal fields, and which will at least confine single particle trajectories. All right. I've said nothing yet about whether or not that field is achievable in practice, which I'm going to talk about now. And I've said nothing about what happens when you put a bunch of particles in and you look at self-consistent electromagnetic interactions between the plasma and this magnetic field, okay, which will be the next topic. So to understand whether or not such kind of well-defined, nice magnetic surfaces exist, what I'm going to do is I'm going to use these magnetic coordinates. So I'm going to use this toroidal flux function again. Think of it as r, basically, poloidal angle and toroidal angle. And for any divergence-free field, you can write that field in this way. So gradient of basically the radial coordinate cross the poloidal coordinate, gradient of the toroidal coordinate cross some function. And at this point, I'm not assuming that this is the poloidal flux anymore. This is just some function of all the coordinates. Okay. And the trajectory of the magnetic field lines, or the equation of motion for those magnetic field lines, is just given by basically the time rate of change of the coordinate is just going to be the contravariant component of the magnetic field in that direction. So xi here is the spatial location of the magnetic field, right, of the trajectory of a magnetic field line. So if I plug in my 3 coordinates here and evaluate this expression, then I get a series of different relations, okay? And what's interesting about those relations, so here I show them for you. You see how the toroidal flux varies with the toroidal angle. And you see how the distance in the poloidal direction is related to the distance in the toroidal direction for the magnetic field, right? So in other words, this is telling you how many times the magnetic field line goes around poloidally for each time it goes around toroidally, right? So it's the pitch of the magnetic field. And so this pitch is actually so important in fusion plasmas that we give it a name. This itself is called the rotational transform. Forget I even said that, because it's going to complicate things. We're going to write everything in terms of this thing called the safety factor Q, okay? So 1 over Q is the pitch of the magnetic field. So why am I going through all this? Well, if you look at these 2 expressions that I've just derived, and we make the identification that this poloidal flux function is a Hamiltonian, the toroidal angle is time, poloidal angle is spatial location, and toroidal flux is the conjugate momentum, then you can see that these are just Hamilton's equations, right? So this is just a Hamiltonian system, and so we can import all the different sort of machinery which has been developed to deal with Hamiltonian systems to tell us something about magnetic field line trajectories, right? In particular, I'm not going to go into all the derivations, but this is, so it's a 1-degree Hamiltonian system because you have one spatial coordinate and its conjugate momentum. And it's called the 1.5-degree Hamiltonian system because the Hamiltonian itself can depend on the time-like coordinate, this toroidal angle, okay? And in such systems, you have 3 possible types of trajectories, which we already knew intuitively would happen. You could have 1D trajectories, 2D trajectories, or 3D trajectories, right? Hasn't told us anything new. What it does tell us is that if we make this a 1-degree Hamiltonian system by eliminating the dependence of the Hamiltonian on the time-like variable, or in other words, eliminating the dependence of the poloidal angle on the time-like variable, then these trajectories are no longer allowed, right? So these are the ones we wanted to get rid of, if you remember. We don't want magnetic field line just wandering around radially inside our toroidal volume. So if we say that this toroidal flux function is not going to vary, for instance, in the toroidal direction, so this was this axisymmetric case I was telling you about, then it's also saying the poloidal flux doesn't depend on theta, it doesn't depend on toroidal angle by the assumption of axisymmetry, and so this poloidal flux is just some function of the toroidal flux now. So we're back down to a 1-degree Hamiltonian system, and so we're guaranteed to have magnetic field lines which can map out toroidal flux surfaces, okay? So we can actually achieve the sorts of configurations that we want to achieve, right? As soon as we get rid of this kind of assumption, we're no longer guaranteed such nice surfaces, okay? And so the types of things that you can imagine seeing are illustrated here. So this is a so-called Poincaré plot of magnetic field lines. And again, you can imagine constructing the toroidal volume by taking this cross-section and rotating it about a vertical axis. And all we're doing is we're looking at where the magnetic field punctures this plane every time it goes around toroidally, okay? So if you do this many, many times, you map out surfaces or, in horrible cases, volumes, right? So you can see these types of surfaces here are nice, well-defined toroidal surfaces. you get kind of funny situations which can happen in which you get regions of the magnetic field which are kind of closed off from all the other regions. These are called magnetic islands. And if you have magnetic islands which overlap, then these magnetic islands can give rise to chaotic behavior and stochasticity of the magnetic field, and that's exactly what you're seeing down here, where you basically have particles which just wander all over the device. Okay? So these are the kind of situations we'd like to have, and we're going to have to work very hard to get them. So basically, the idea now is that we have two different possibilities, right? Both of them are tori. One of them is this possibility in which we have an axisymmetric magnetic field, and in which the current inside the plasma is generated by some transformer coils in the middle. So this is called a tokamak. And it's good because, as we saw, if you have axisymmetry, these drift orbits are confined, you're guaranteed the existence of flux surfaces, and it's much easier to design and construct because of the symmetry in the problem. The alternative is to look at something called a stellarator, and in this case you have these, again, the poloidal field is generated not by current through the plasma, but by these funnily shaped coils. And of course this is much more complicated to construct, but at the same time it means you don't have to put a current through the plasma. And first of all, that means that you can have a steady state system, because remember, this was inherently not steady state. And second, it turns out that whenever you put a current through your system, you can drive instabilities. So this might be a bit better for stability, but it has this difficulty that you have to work really hard to try to find configurations which approximately confine these drift orbits. You aren't guaranteed the existence of flux surfaces, so again, you have to work really hard to try to construct approximate flux surfaces, and it's just very complicated to deal with, right? But at the same time, you also have much more flexibility in all the different plasma shapes. I mean, you can imagine there are many, many, many more possible shapes which look like this than look like this. And so it's possible that such shapes might be able to optimize, for instance, stability. Okay. So for the moment now, let's imagine that we have some kind of magnetic surfaces which exist in our plasma. We can obtain them in some way. How do we get them to stay around? So we want an equilibrium for our plasma, and we can obtain that equilibrium equation simply by taking the kinetic equation and taking the velocity moment of that equation. So that's all I've done here. I've taken the kinetic equation, taken the velocity moment, and I've used the continuity equation to clean things up a little bit. All right. So what we have here is the change in momentum. We have a divergence of a pressure tensor, Lorentz force, and this is the force due to collisions between different species. So this is the momentum exchange. So we're looking for an equilibrium, which means that we want this term to be 0. And what we're going to do is we're going to take this equation and sum it over species. And when we do that, because momentum is conserved, it means that if you sum over the momentum exchange between species, that net exchange is going to be 0. So all we're left to deal with are these three remaining terms. So first, let's look at the field which involves the term which involves the electric field. What we're going to find is that this term doesn't contribute due to something called quasineutrality. And quasineutrality basically is telling us that the charge density of the plasma is essentially 0. Okay? Why is it 0? It's because the plasma is really, really efficient at responding to any electric field which arises. So particles are going to stream through the plasma to cancel out any electric fields which try to arise. Okay, so let's rearrange their distribution. And how do we see that? Well, here's Poisson's equation. So it tells us the divergence of the electric field, so phi is the electrostatic potential, is equal to the charge density. And if we take the scale of variation of our electrostatic potential to be L, and we basically say that density fluctuations are going to have the same size that you would expect from, say, a Boltzmann response in the plasma, then the charge density looks like this. It goes like the electron charge density times the ratio of the Debye length of the plasma to this scale variation of the electrostatic potential. Right? So as long as the electrostatic potential varies over scales much larger than the Debye length, which is true for certainly all magnetic confinement fusion plasmas, then this charge density is very small compared to, say, the charge density of any given species, right? So in other words, whenever I sum this over all species, the total charge is going to be neglected. This term we're going to simplify by basically assuming we're near thermodynamic equilibrium always, right? Why is this justified? Well, it's because we assume that we have the plasma confined for a very long time, right? So over the time scales that we care about, i.e. the confinement time, we assume that even though the collisions may be fairly infrequent, they're still much more frequent than the confinement time, which means that the plasma has time to relax to a thermodynamic equilibrium before it evolves, right? So instead of having a pressure tensor, I'm just dealing with a gradient of a scalar pressure. And so when I take these things into account, I sum over all species, all I'm left with is the pressure gradient term and this J cross B force, where J here is the total plasma current, right? So what is this really telling us? Because we have a cross product here of two terms, it's telling us that I can dot the left-hand side with either of these vectors, and I'm going to get 0, right? So in other words, the pressure is constant along magnetic field lines. So whenever I look at one of these toroidal surfaces, the pressure is constant on that surface. So for instance, I can use it to label flux surfaces. And furthermore, the current also, the pressure doesn't vary in the direction of the current. Right. So the picture you should have in your mind is that you have these toroidal surfaces, the plasma pressure is constant on those surfaces, and the current is completely contained inside that toroidal surface, right? There's no radial current in the plasma. So physically speaking, what is this telling us? It's simply saying that if you're in the collisionless limit, particles can stream rapidly along field lines and equilibrate before things propagate out radially. Or if you're in the very collisional limit, it's saying that sound waves can propagate along the magnetic fields and equilibrate things within a flux surface before the confinement time. So I've kind of given you an unintentional preview of the result here, but another consequence of this quasi-neutrality relation that I showed you earlier is that the divergence of the current is 0, okay? And that comes from looking at charge conservation and estimating the size of this charge, which is basically what quasi-neutrality was doing. And so if we use this estimate for the charge density that we just derived, plug it in up here, then we get the divergence of the current goes like the charge density over some time scale. And plugging in this expression, we get this relation between the Debye length and some macroscopic length scale in the plasma, as we did before. And now, if we try to see how big this quantity is compared to, say, the naive estimate. So the naive estimate would be to say that this thing scales like the current over the length scale associated with the current. Then we see that there's actually another factor multiplying it, and that's the ratio of the electron thermal speed over the speed of light. And this here is the electron Larmor frequency. So this is going to be small, partially because the electron thermal speed is not usually relativistic. It's maybe around 1/10 in many fusion plasmas. And also because this electron gyration is incredibly fast compared to all the other time scales of interest, especially on the equilibrium time scales in the problem. So this divergence of J is effectively 0, right? And why do I care about that? It's because if I look back at my equilibrium equation, gradient of pressure is balanced by the J cross B force. This is necessarily the perpendicular current which enters, because any parallel current when crossed with B is 0. And so we must have some perpendicular current in our plasma in order to have an equilibrium, right? If I take the divergence of this perpendicular current, you're going to find it's non-zero, but the total divergence has to be 0, and so that tells us there has to be a parallel current in the plasma as well, all right? And this is important because it affects the stability of the plasma. So there has to be some parallel current. This parallel current is going to give rise to instabilities. So we can recast this equilibrium expression that I derived for you guys in a different way, which might be a bit more physically intuitive. So if we define this kappa, which I'm showing you here, which is the curvature vector, to be b hat dot grad b, where this little b here is the unit vector in the direction of the magnetic field. And you can see why this is the curvature vector if you look at a simple case. So if we have a magnetic field, it's just a circular magnetic field in this, say, phi direction. Then the unit vector phi hat dot grad phi hat is just the derivative of phi hat in the direction of phi. So in other words, how does this vector change as I move along phi? And that's some vector which is pointing inwards, okay? And it has some magnitude which is inversely proportional to where I am. So in other words, if I have a bigger circle, then this curvature vector is smaller, and it's always pointing radially inwards. So this curvature vector, again, if I use some vector identities and use Ampere's law, I can write the curvature in terms of this J cross B and the gradient of the magnetic field. So if we use our equilibrium constraint to replace J cross B in this expression, then we can massage things a little bit, and we end up with this force balance expression. So what you can see is on the left-hand side, you have something which has to do with the curvature of the field lines. In fact, what this has to do with is it's a force which, if you have a magnetic field, and it's in some kind of circular shape, right, and you try to stretch that magnetic field out to a larger radius, for instance, it acts a bit like a rubber band. It has tension in it, and so whenever you stretch it like this, it's going to try to have a restoring force which opposes that motion. So that's exactly what this force is. It's some kind of tension force in the magnetic field. And then you have forces over here on this side which come from gradients in the pressure and gradients in this b squared, which, because of its similarity to the scalar pressure here, is called the magnetic pressure. So in equilibrium, the total pressure gradient, the sum of these two things, is going to be balanced by field line tension. And because beta is much less than 1 in fusion plasmas, then really you can typically neglect the plasma pressure in this expression. And so the dominant balance is simply between field line tension and magnetic pressure. So what I want to do now, we have some abstract expression for an equilibrium. And so what I'm going to do is I'm going to look at this sort of simplified case of an axisymmetric equilibrium, partially because it's much simpler than the general case, and also because these axisymmetric devices, or Tokamaks, are really kind of the most widely used type of fusion experiment these days. So what I want to do first is I want to look at the radial component of Ampere's law. We hear this superscript r denotes, again, the contravariant component of the current. And so I can write that in this way. It's just curl of B, which is here with the Jacobian. This is the Jacobian of the transform from kind of Cartesian coordinates into these magnetic coordinates, where R now, it doesn't really matter what R is. R is just some coordinate which is a flux label. So it could be the pressure, it could be the toroidal flux, colloidal flux, whatever. So the fact that our equilibrium condition tells us that there's no current in the direction of varying pressure tells us that the radial current has to be 0 unless the pressure gradient is 0. So assuming that we have some pressure gradient in the plasma, in other words, we assume it's hot in the middle and cold at the edge, then there's no radial current in the plasma. So the left-hand side of this expression must be 0, right? Because we're assuming axisymmetry, we know that the magnetic field strength also is not going to vary as I move around toroidally in the plasma. So this term is gone, and it tells us that then the toroidal component of the magnetic field doesn't vary poloidally, all right? We also know from the axisymmetry assumption it doesn't vary toroidally. So in other words, this toroidal component of the magnetic field only depends on sort of this flux label R, right? And so as a result, we can write the magnetic field in this way. So this was just the covariant component of the toroidal magnetic field. So I'm going to call it I, just by convention, for whatever reason, people call the toroidal component of the magnetic field I. So here's our general form for a magnetic field in an axisymmetric system. So what we can do now is we can take this form for the magnetic field and plug it back into our equation for force balance, right? So our equilibrium constraint. And so again, our equilibrium constraint in these coordinates just looks like some p prime is the derivative with respect to this radial coordinate r. It involves the colloidal magnetic field and the toroidal and colloidal currents in the plasma. And remember, this q here is the safety factor, so it measures the pitch of the magnetic field lines within a flux surface. So I'm not going to go into all the details. There's much algebra, which is always associated with these toroidal calculations. But the idea is that we can calculate both the toroidal and the colloidal components of the current simply from looking at Ampere's law. And after many vector identities, one finds some expressions for these currents in terms of, say, the colloidal flux in the plasma, this toroidal field, or I, and the safety factor Q. Right? So if I take these expressions, I plug them back into my radial force balance, then what I find is this expression here. So on the left-hand side, this is the toroidal current, and then on the right-hand side, we have other bits. This is called the Grad-Shafranov equation. All right? So this is the equation one has to solve to understand equilibrium in an axisymmetric toroidal plasma, or Tokamak. And it's kind of a funny equation. So first of all, let's do a little manipulation. I'll tell you why this is particularly funny. So we can write this, for instance, in cylindrical coordinates, where r is that major radius of the torus. Z is just, for instance, the axis of symmetry, so it's the vertical direction. And when you do so and make this substitution, so I rewrite, instead of using the colloidal flux, I use some function u here. This makes this thing look a bit nicer. And so what we have is a Laplacian of u equal to some stuff on the right-hand side, okay? So this is a Poisson equation. Numerically, because this is a school focused on computation, Poisson equation is something which is solved routinely, and there are many, many different approaches for solving this numerically, okay? It can be solved as long as you're given, say, the pressure as a function of u, this toroidal field as a function of u, and some boundary condition on u, right? It's a bit more complicated than that because if we're solving for u, these profiles have to be specified in terms of u. So you don't know u, but you have to specify the profiles in terms of u. So in practice, what you can do is you can put in some initial guesses. So let's imagine you know, say, the pressure and the toroidal field in terms of real space coordinates, so x, y, and z. Well, you can kind of guess what the mapping is between u and real space coordinates. You can write down what this pressure gradient is and what this, this gradient of I squared is, and you can solve for u, right? Now you can go back and test. Does this dp du actually satisfy what you thought it should satisfy? In other words, if I look at dp dr, where r is some real space variable, is it consistent with the dp du that I've just found, given that I now know what u of r is, right? And inevitably, it won't be at first. And so you then correct this. And so you can iteratively solve this equation by each time updating your understanding of what u is in terms of r until you get something which is self-consistent. And so there are many different solvers in the fusion community for obtaining this equilibrium, which take different approaches. I'm just going to quickly give you a flavor for one way of doing it by showing you a recent sort of attempt at doing this numerically. And this is due to researchers at NYU at the Cron Institute. So the basic idea is that in general, these toroidal surfaces might be quite complicated. So again, you rotate this around this way and you get your torus. So the shape of these constant magnetic field, constant flux surfaces can be quite complicated. Solving on this complicated domain is non-trivial, right? And getting accuracy is therefore an issue numerically. So what you'd really like to be able to do is not solve on this domain, but solve on something much nicer and simpler like a circle, right? And you can do this. So if we have a problem, we're trying to solve for the Laplacian of this u And on the right-hand side, you have some function of the coordinates. Well, we can actually define a conformal mapping which takes this shape and projects it onto just a circle. Okay? And when you do that, you're no longer solving for your function u, you're solving for some slightly different function, say v, which is a function, again, of some mapped coordinates. I'm not going to go into all the details of this conformal mapping, but the basic idea is you can take some Poisson equation and turn it into a different Poisson equation on the circle. And the boundary condition also is appropriately mapped. So the nice thing is now, because this is a periodic domain, you can use a spectral approach in this angular coordinate, right? In particular, we can write things in terms of Fourier components because the Fourier components are guaranteed to be periodic. And the thing that coming to the circle buys you is the fact that on the circle, we can easily just put down equally spaced grid points here, and you can Fourier transform this very quickly on a computer. So there's something called the fast Fourier transform, for those of you who may be aware, which requires equally spaced grid points to be fast. So the idea is you transform from your complicated domain onto this circle. You expand in a suitable set of basis functions, i.e. the Fourier modes. And you plug this ansatz back into your equation. And by doing so, you basically decouple all these different Fourier harmonics. And you reduce a partial differential equation into an ordinary differential equation. Right? So you solve this on this domain. You get what Vn is. You map it back onto your original domain, and you have your solution. Okay? So it's a neat way of solving a complicated problem. And at this point, with an ordinary differential equation, again, there are many different ways you can try to solve this. They do something very clever, but I'm not going to go into all the details here. So as usual, whenever you do something clever, there's always the possibility of things going wrong. And so one problem with something like this is that you have this nice uniform grid here in the mapped domain. But whenever you go back to the original domain and you look at which grid points this corresponds to, you can end up getting situations in which you have relatively few points sampling parts of your domain and a lot of points sampling other parts of your domain. And depending on the shape of this surface, it can be kind of okay and not a problem. I mean, clearly, if this were a circle, then there's no bunching at all that occurs. But you can imagine very funny shapes in which you could get very poor resolution over parts of your surface. So you have to be careful about this sort of bunching effect. So this was something which is due to, as I said earlier, these researchers at NYU. So the point of the Grad-Shafranov equation is solving for this poloidal flux function. And I told you that to do so, you need to tell me what the profiles of this toroidal field and pressure are. But how do we get those things, right? Well, it turns out that you have to calculate a couple different things to do so. You have to calculate the pressure somehow. And to get the toroidal magnetic field, basically you can get that in terms of the parallel current that I mentioned to you earlier. And so I'm not going to go through the analysis, but the same sort of tricks we use to get the Grad-Shafranov equation can give you an equation not only for the toroidal current, which is what this is, but also for the parallel component of the current. And so you can see this is also some function of I and P, so we have one new equation now. And the parallel current we're going to get by taking some moment of the equilibrium distribution function. All right, so somehow we're going to have to get what this is. I'll come to that in a minute. And we have to get the pressure profile, which we get by taking the energy moment of our kinetic equation, and that tells us how this equilibrium pressure slowly evolves in time on the energy confinement time scale. And it'll depend on fluxes of energy out of the domain and sources, which involve things like heating, possibly due to actually directly injecting heat into the plasma. You can imagine turbulence heating the plasma. You can imagine things like collisional temperature equilibration turning up on the right-hand side here. And the difficulty with this problem is that to calculate both this distribution function and these fluxes requires a kinetic treatment of the problem. Okay? So far, all we've had to deal with is fluid dynamics, and everything's been fairly straightforward. But this kinetic treatment is going to significantly complicate things. And so this is going to be the topic, basically, of Friday's talk. I'm going to talk about how you get sort of this equilibrium distribution and how you calculate the turbulence, which is what gives rise to these fluxes. So in theory, that closes the problem, right? From what I've just shown you, we can obtain the toroidal flux, we can obtain the toroidal field, we can obtain the pressure profile, and we have an equilibrium, we're done. Of course, the question is whether or not the equilibrium is going to stick around if you perturb it in any way. And so we have to look at the stability of our equilibrium to fluctuations. And so in these toroidal plasmas, you can imagine, there are an entire zoo of instabilities which can arise, right? And because of the toroidal geometry, things become incredibly complicated, simply because you can't decouple modes anymore. Because the field strength and many things vary along magnetic field lines, it turns out that a simple sort of Fourier decomposition of the perturbations into different modes doesn't lead to a decoupling of the modes. So all the modes couple, and it's a mess. Okay? So there's no way I'm going to go through some sort of comprehensive analysis of stability, so I'm going to talk to you a bit about sort of the physical pictures of how they arise. And in particular, I'm going to talk about sort of the most unstable type of modes you might expect to find in the torus. So the guiding principle in doing all of this is that, as we saw for the equilibrium problem, you have a few different forces which are acting in the plasma, right? We have things like pressure gradients, which can try to make the plasma volume expand, which is not what we want. You can have parallel current, which will drive instability, as I'll show you in a minute. And sort of the one bright spot here is that you have field line tension. So the tension itself is going to try to oppose the expansion of the magnetic field lines. And so, broadly speaking, the most dangerous instabilities are the ones which don't actually try to bend the magnetic field lines. Okay? So what does that mean? It means that they're aligned with the magnetic field. Or in other words, their parallel wavelength is much, much longer than the perpendicular wavelength. Right? So I'm going to illustrate that here in this plot. So what I'm showing you here is this idealized example where all I have is a purely toroidal field, which recall is not what we're actually going to have, but it's very difficult to visualize things on a helical surface. So imagine we have purely toroidal field lines here, and we're going to perturb it by making k parallel equal to 0. And so we're only going to perturb the field perpendicular to the field line. Right? So in other words, what you're going to get are these sort of flute-like perturbations, they're called, because they look like fluted columns. And what these things do is they don't in any way bend the magnetic fields. So there's no stabilizing tension to kind of cancel them out. And what we should note is that, of course, in a real device, there's going to be these poloidal component to the field. And these field lines, in general, will end up mapping out what are so-called irrational surfaces. So in other words, they're going to go around toroidally and poloidally, but they're never going to match up on themselves, right? They'll come infinitesimally close to every point on the surface, but not actually overlap. And so it's not possible to have k parallel equals 0 on such a surface, right? The only way you can possibly have k parallel exactly equal to 0 is if you actually have sort of a single-valued function there, in other words, is a way of saying it. So you have to have rational surfaces where the magnetic field lines go around and eventually close on themselves after some number of times, right? In that case, you can actually define a perturbation which is always having k parallel equal to 0. Otherwise, let me put it one other way. I don't think I've said it very well. If you have an irrational surface, a single magnetic field line maps out the whole device, right? So if you have no k parallel, then you have no k perp, because the magnetic field samples the entire surface. Okay? So why are these particularly dangerous? I've given you some heuristic example here, but let's look at the type of instability that appears if you do this. So we take our flute-like perturbation, and let's imagine what happens out here on the outside of the plasma column. So whenever the plasma is moved outwards in this location, we can see that the magnetic field strength has gone down, right? Because the magnetic field strength increases as I go towards the center of the torus. So you have rarefication of the magnetic field lines out here, whereas in this region, you can see that the plasma is moved inwards, so you have compression of the field, and therefore you have basically forces which are trying to keep the plasma in place here, and you've weakened the forces keeping the plasma in place here, and so as a result, the plasma squirts out this way and is further compressed in these regions, right? So this accentuates the initial perturbation and gives rise to some kind of instability, which is called an interchange mode. The reason it's called interchange is because fundamentally what it's doing is it's interchanging volumes of plasma with volumes of magnetic flux. And so things seem pretty bad, but they're not quite as bad as they seem, again, because you have this poloidal field in the torus. So if I repeat the analysis I just did, but I do it now on the inside of the plasma column, what do I see? Well, here, where the plasma has been shifted inwards, again, the magnetic field lines, magnetic field strength is increased, and so effectively you're compressing the magnetic field in this region. Here, the magnetic field is decreased, and so you're rarefying it. And so, again, the plasma tries to squirt out in this region and is confined in this region, and so you can see that that's opposite to the original perturbation, right? So this is a stable situation. So people will then talk about so-called good curvature and bad curvature. So in the original case, we had so-called bad curvature. This is when the magnetic field lines curve towards the plasma. And so it's in that kind of situation in which you have instability. And in this case, the magnetic field lines were curving away from the plasma volume. And in that case, you have stability, right? So you have good and bad curvature. And in a torus, you'll have regions of both as you move along the field line. And so what you end up finding is this so-called ballooning picture. So if you move along the magnetic field, so say this is at say this location in the plasma. Here you have bad curvature, and so you have instability, and so you'll have some radial wandering of the plasma. Whereas on the inside of the device, so in here, things are stable, and so you get no perturbation amplitude, right? So in other words, you're seeing the plasma balloon outwards over some small region in the bad curvature region of the device. Now, the nice thing about this is that so even if initially you set up a perturbation which wasn't bending the field line at all, what you're doing here is you're pinning the field line in one region of the plasma, and you're allowing it to expand out radially in another region of the plasma. And so even if you don't have field line bending to begin with, you develop field line bending to satisfy the good curvature and bad curvature conditions, right? So this itself is self-stabilizing to some extent. The other thing that helps is the fact that, let's imagine that I start out with some surface. So let's consider this surface for a second. And imagine things like this. So there's magnetic field lines which are moving in this way, and so this is a perturbation which doesn't bend the field line at all, right? Now, this is at some radial location, say, in my plasma, but if the pitch of the magnetic field line changes at different radial locations, which it does, then it turns out that the magnetic field lines are now pointing in a different direction as I move radially. And so the type of perturbation I need has to change as I move in radius. In other words, if this perturbation satisfies this flute-like condition at one radius, then just next to it, it doesn't, right? So this also has a stabilizing effect whenever the pitch of the magnetic field line changes as I move radially, which is called magnetic shear. So the other type of instability, I've been talking about basically interchange mode so far. You can get instability even if you don't, even with field line bending. And one example of that is a kink mode, so-called kink mode. This comes from helical perturbations, and this is what comes from that parallel current which is sitting in the plasma. And again, there's a simple picture that you can use to kind of describe how it works. So if this is some volume of plasma, which again you would imagine turning this into a torus. And you have magnetic field lines which are moving around helically here. If you just take this plasma volume and you kink it, right, just like you would take a hose and kink it, then what you see again is that here you're pressing the magnetic field lines apart, and here you're pressing the magnetic field lines together. So you're compressing the field here and rarefying it here. Again, what that means is that now you've already pushed the plasma this way, and now you've made it easier to push the plasma that way. And you're making it such that the plasma wants to be pushed in this direction due to the compression. And so once you start kinking, it continues to kink, and it grows and grows in amplitude, right? Again, the way to get around this is to realize the fact that there is some field line bending when this happens. And so you try to set up equilibria in which the field line bending can stabilize this effect. Okay, so those are the physical pictures of the type of instabilities we have in these toroidal plasmas. We have these interchange instabilities where you just move around magnetic flux and exchange it with parts of the plasma, which in a toroidal system with a poloidal field ends up giving rise to these ballooning-like instabilities. And you also have current-driven modes called kinks. So in theory now, in order to actually find out if your plasma is stable in practice, what you would do is go through the procedure that Matt will have laid out on Monday. You'll write down your MHD equations, say, here I'm going to be focusing on ideal MHD, but you can put in corrections to it. You linearize those equations. You can assume they go in time like e to the I omega t. You get some kind of linear set of equations, which is an eigenvalue problem, and you solve it. Okay, when you do that, so that's what I'm doing in a way here. I'm writing down the momentum equation. I can write the perturbed flow. So anything with a subscript 1 here is a perturbed quantity, and anything with a subscript 0 is an equilibrium quantity. So if I write everything in terms of this displacement vector xc, so this is the displacement of the plasma and the perturbation, then the left-hand side of this thing just becomes minus omega squared times charge density, times mass density, times displacement is equal to some force, which is this J cross B force and the pressure gradient force. All right. Now, it turns out that in astrophysical plasmas, this is a convenient way of doing things, right? You solve the eigenvalue problem, you see what modes are unstable. But as I pointed out, in toroidal plasmas, all these modes couple. And so it's not quite as convenient to decompose things in this way. And so it turns out that there's something called the energy principle, the MHD energy principle, which will make calculations of stability a bit easier. And so I'll go through how we obtain that. So I can write the kinetic energy of the associated with the perturbation in this way, and the potential energy associated with the perturbation in this way. You can see this is just displacement dotted into force. So this is the work done by the displacement in opposing the force. And so the eigenvalue problem you can recast in terms of a variational principle. So we have our potential and kinetic energy expressions. I can define something, which I'll call big omega squared, not to be confused with cyclotron frequency, as the ratio of these two energies. And I can look at what happens whenever I vary this quantity, and I set it equal to 0. So I'm going to find an extremum of this. So I'm not going to go through the details. It's fairly straightforward if you want to try it. But basically, to do this, all you have to do is everywhere you find displacement xc, you just set it equal to xc plus delta xc, right? And whenever you do this, you find this expression here on the left, right? So if I now define delta w over k to be omega squared, then this reduces to the original eigenvalue problem, right? So all I've shown you here, and I've only kind of shown it to you because I haven't shown you all the steps in between, is that this variational principle form of things is identical to solving the eigenvalue problem, which you're probably all familiar with, okay? But this in itself wouldn't really make things much easier for us. What makes it easier for us is the fact that these instabilities are large-scale macroscopic instabilities, and we want confinement, right? So I don't really care what the details of the instability are. All I want to know is, are things going to be stable or are they not going to be stable? If they're not stable, the equilibrium is going to fall apart really quickly, and it doesn't matter if it fell apart on a time scale of a microsecond or 2 microseconds. It's still too short. So all we really care about is whether or not there are any modes which are unstable. And so with that in mind, we can only look at this potential energy, for instance, this delta W, make use of the fact that we know what this force is in here, and we can just write the displacement, say, as a sum of Fourier modes. We can plug that back in here, and we can get some expression for delta W. All right, and then I'll show you in just a second that if delta W is negative, that means things are unstable, and if it's positive, they're stable. Okay. Now, in doing this, I've swept something under the rug simply because it's sort of an unneeded complication at this point. In reality, it turns out that in MHD, there's actually a continuous spectrum of modes. And here I'm assuming there's some discrete spectrum, right? This has some effect. It turns out that you can still derive this energy principle even with a continuous spectrum of modes, but it's much more complicated, and I don't want to go through it here. So if you take this simplified approach, put in the displacement, plug it in, delta W then is just a sum over all these different modes of this coefficient, modulus squared, times the frequency of the mode squared. Okay? So what does this have to do with stability? Let's imagine that delta W is negative, right? Well, if delta W is negative, all these things are positive definite. And so for this to be negative, at least one of these omega squareds has to be negative. And omega squared being negative implies that this has some e to the positive number times time sitting there. So in other words, you have instability whenever omega squared is negative, which means you have instability if delta W is negative. On the other hand, what happens if delta W is positive definite, right? And if it's positive definite, not just for some particular displacement, but for any displacement I can think up. Well, in particular, I can always choose a displacement which is one which satisfies that all these modes are 0 except for one of them, right? Perfectly valid. In that case, we see that delta W is just omega squared for that particular mode, and we know it has to be positive. So that means delta W squared has to be positive for that mode. And since I chose that mode at random, this is true for all the modes. So in other words, if delta W is positive definite for all displacements, then that tells us that the plasma is stable. So this is a proof that if delta W is less than 0, things are unstable. If it's greater than 0, they're stable. So in practice, how does this help us? Well, I can take my delta W, write it in a way very similar to the one I just wrote it. So I can write the displacement in terms of the sum of some kind of appropriate basis functions. Plug it in here and see what I get. And so I see that delta W is a sum over some modes of this expression. This I can calculate. These are just basis functions. I know what those are. I can just plug them into this expression, use the form of f that comes from, say, ideal MHD, and evaluate this quantity. Right? And then the trick becomes minimizing this function. So the problem of determining whether or not the plasma is stable is reduced to a problem of numerically minimizing a function, which there are many, many different ways to do, right? So this is in practice the way that many different codes in the fusion community check for MHD stability. So that's basically it today. The question is, what's left to be done? So what we found is that if you want to have a confined plasma, it needs to be a torus. That torus needs to have both toroidal and poloidal components of the magnetic field. And that if you choose the symmetry direction, for instance, while not necessary, it will guarantee you to have nice magnetic surfaces in your plasma. Okay? You won't have stochastic regions, for instance. For that matter, we also found that these things can be unstable, but for instance, if you pick your equilibrium nicely, then you can try to minimize such instabilities. And so in theory, everything's kind of okay. We can come up with equilibria. They're mostly stable, but mostly is part of the problem, I guess. So what are the problems with this? First of all, Tokamaks, even these axisymmetric devices, are not exactly axisymmetric, right? Somehow you have to generate them. You generate them with a discrete number of coils which run current through them. And so there are some deviations from axisymmetry, and those deviations can be important. That can give rise to breaking of these magnetic surfaces, reconnection, forming of islands, and stochasticity. And so we have to work hard to avoid that. Also, these stellarators, which have some significant advantages, such as steady state operation, it's very difficult to come up with configurations which work for stellarators, right? And so numerically in particular, it's quite challenging to come up with numerical equilibria for stellarators with things like islands and stochasticity in them. Most of what I've been telling you, for instance, about stability was in the context of ideal MHD, and in equilibrium, if not ideal MHD, at least it was not kinetic. And so there are, of course, some corrections to what I've been telling you, to this grad P equals J cross B, and these things, it's unclear what effect they're going to have or how important they might be. We also saw in the video that I showed you that occasionally these large MHD instabilities that happen in the plasma, even if you work really hard to eliminate your MHD instabilities, it turns out that occasionally something's going to go wrong, right? While this is okay on current devices, as you get more and more energy content in your fusion devices, then having some instability which takes all that hot plasma and just flings it out to the edge of the wall is not such a good idea, right? So for instance, in ITER, which I'm guessing many of you will have heard of, if you have something like a disruption due to one of these MHD events, and it flings all the plasma into the wall, ITER's gone. Just one of those and it's done. So we have to be extremely careful in coming up with ways to avoid these things. And if they are going to happen, we can even trigger them intentionally before the energy in the plasma gets too big, so that you don't have that much energy which leaves the plasma. So there's a whole range of things people try to do to ameliorate these MHD instabilities. And so the final thought I'll leave you with, which leads us into my talk on Friday, is that even if you have so-called good magnetic surfaces, right, so you don't have islands, you don't have stochasticity, and if you have some MHD quiescent plasma, so you've been very clever and you found a way to have no macroscopic instabilities in your system, then you're still going to end up with problems with confinement, because even though you might be stable to these large-scale instabilities, there's always going to be a free energy source in the plasma because you want to have gradients in things like density and temperature. And so you're pretty much guaranteed to have some kind of instability in the plasma. And what we try to do is limit that instability to small scales. These are called micro instabilities. These involve kinetic effects and kinetic physics on the ion-Larmor scale. And the turbulence that results from these instabilities slowly diffuses the heat and particles out of the device. And so a large part of the effort in the fusion community these days is trying to understand how this turbulence works and to figure out if there's ways to minimize the resulting transport from it. So that'll be what I talk about on Friday. Thanks. Everything crystal clear.